This is week 3 and we will cover, this is week 4 and we are going to cover important topics today. We will mention chain rule, implicit differentiation, logarithmic differentiation, and some new rules for natural logarithm and natural exponential functions. So let's start with the chain rule. The first question on this template is about taking the derivative of composite functions, which can be handled by using chain rule. So let me put a recall. Let me start with a recall about chain rule. Chain rule is a tool that helps us to differentiate compositions of functions. What do I mean? For example, this is a composition function, right? G composed with F. And I want to take the derivative of it. And there is a very special rule to handle this derivative, which is called as chain rule. You start with the most outer function. Okay, here, the most outer function is G, right? You start by taking the derivative of it, and then you write whatever function you see inside. You don't touch it. And then, according to rule, you need to keep multiplying with the derivative of this insider function, like that. This is what we call as the chain rule, and it should be applied to find G prime in the first example. Okay, look at the function. Can you tell me what is the most outer function here? Obviously, GT is a composition of different functions, right? And I think the most outer function is taking this power minus 1 power. And we know how to deal with taking powers, right? Everyone knows how to take the derivative of taking minus 1 power of something. So we will first take the derivative of this power function. What I mean is minus 1 comes down, then you don't touch the insider function sine 3t divided by 3 minus 2t, and then I subtract 1 from the power. You see, I didn't touch the insider function, but what I did was taking the derivative of the minus 1 power. And then what should I do? I should keep multiplying with the derivative of this insider part. Okay, let's write this down. Sine 3t divided by 3 minus 2t, I need to multiply this first expression by the derivative of the insider part. Okay, let's try to handle this derivation. You know, this is a quotient function. That's why we need to apply quotient rule. Okay, so who remembers the quotient rule? If you have an expression like that, ratio of functions, then the derivative rule goes like that. Fg prime divided automatically by the square of the denominator. This is the quotient rule, and I will apply it for taking the derivative of this ratio. Derivative of 1 plus sine 3t is, derivative of 1 is just gone. It is just 0. Sine 3t, derivative of sine is cosine. You see, I'm applying a small chain rule here. I don't touch inside, and then I need to multiply with the derivative of this insider function, which is 3. So this is the derivative of the numerator times the denominator. I am applying this rule now. Minus, numerator stays the same, sine 3t. This is numerator times the derivative of the denominator. What is the derivative of the denominator with respect to t? It is minus 2. Divided automatically by the square of the denominator. This expression squared. And this big whole expression is the derivative of the insider function. And yeah, that's the result. This expression times this one, the red one, gives you the derivation rule for GT function. And we applied chain rule here. Is everything clear? Any questions? Okay, let's move on. If not. Second example, again, y is given as a composite function inside one another. There are lots of functions and we want to compute y prime. first derivative of y. I think this recall would be nice here. How do you take the derivative of the square root function? We used this derivation rule last week, I guess. It is 1/2 times itself. You can easily derive it by yourself by seeing square root as the 1/2 power. So what if now I put not just x, but a function depending on x inside square root? Then chain rule you should apply. According to chain rule, you will start with this most outer function, which is the square root function. You know how to deal with square root while taking the derivative, right? 1/2 times itself. You don't touch the insider function. And then what you should do is you need to multiply with the derivative of the insider function times f prime of x. So this is the rule for handling square root functions in this form that has another function itself. Okay, look at our particular example. The most outer function is square root, and inside there is another function to deal with. So we will start with the most outer function, which is the square root. So I am applying the rule for taking derivative of the square root function. 2 times itself. I don't touch the insider function. I just write it as it is like that. Okay, so like this. And then this should be multiplied with the derivative of the insider function, right? Times, I need to multiply it with the derivative of this insider part. Okay, let's put that down. 3t plus 2 plus 1 minus t square root. I need to multiply this first expression with the derivative of this one. Now let's deal with the derivative of that expression. How can I handle it? Okay, let's deal with it. 3t is derivated as 3, obviously. And now another square root function is the most outer function. We again apply derivative of the square root. So 1/2 times square root itself. This time the insider function is this one. I am writing it as it is without changing anything. Times the derivative of this expression. Times the derivative of this. I don't take the derivative yet. I will just write times the derivative of it, right? Okay, now what is the derivative of this expression? It is not that difficult. 2 is gone, 0 plus, you know how to deal with derivatives. 1/2 times itself, don't touch inside, and then you need to multiply with the derivative of this most insider part, which is, what is the derivative of 1 minus t with respect to t? It is -1, okay? So this black expression times this blue, red expression, blue one and the green one, from beginning to the end, gives you the whole derivative of the given function, okay? Any questions? Step by step, by applying chain rule, you can handle any given expression with the derivative, okay? What we applied here is the chain rule. No matter how complicated the function is, step by step, applying chain rule, you can find its first derivative. Any questions? Otherwise, I want to move on. Okay, so let's move on. This time, we want to find y prime again, but be careful, y depends on theta, and we are taking derivative with respect to theta here, not x, but theta. You should notice something. Notice that y is given as a product. Okay, so this is a product function where this is f, and let's call this second part as g. And you should recall that we are applying product rule for this type of structures. How do you take the derivative of such a product? It goes like f prime g, f g prime. Okay, let's apply that. dy over d theta is, derivative of theta with respect to theta is 1. So this is f prime times g. G is written as the same, cosine ln theta, and then plus f stays the same this time, f times g prime. Okay, let's try to write g prime here inside this parenthesis. Sine, derivative of sine is cosine. You don't touch inside, cosine ln theta. Now you need to multiply with the derivative of this insider part, which is 1 over theta, plus, and you do the same for the next one. Derivative of cosine is sine, sorry, minus sine ln theta times, okay, let me also write this part better. Okay, minus sine ln theta times 1 over theta, because you also need to multiply with the derivative of ln, which is 1 over theta. So this is g prime. What happened here is, this is f prime times g plus this is f times g prime. We applied product rule, which is given like that. F prime g plus fg prime. Is everything fine with this example? And maybe I can also recall you the derivation rule for ln x. It is 1 over x. Okay, can we move on? Is it okay? Let's move on, no questions as far as I can see. Okay, here in this part, we are going to cover some new rules for exponential functions.
Okay.
Okay, so I already used this rule in the previous example. The derivative of ln function is given as 1 over x. And now let's concentrate on some other rules. Like, okay, let me put a recall here, like a to the power x. Let me start with a more simple expression. How do you take the derivative of such functions, x to the power a? What kind of function is this? This is a power function, right? And we know how to take the derivative of powers. You take the power down, you subtract 1 from the power. What if I change the roles of x and a? Then can you still apply power rule like that? Does it make sense to you? Is this correct?
No.
No, I cannot. You are right. I cannot apply power rule anymore because of the simple reason that this is not a power function anymore. This is an exponential function and it has its own rule. Instead of doing this very wrong expression to take the derivative, you need to apply exponential rule for taking the derivative for this exponential function. So its rule is itself times ln a. This is a new rule for us, okay? Itself times ln a. Then I want to make the situation a bit more complicated by putting f of x instead of x, a function depending on x, I put to the power. Then can you guess the derivation rule for this expression by using chain rule? Okay, so chain rule will be applied here. Normally the derivative of the exponential function, which is the most outer function, goes like in this rule. Itself times ln a, and then according to the chain rule, you need to multiply also with the derivative of this insider part, which is f prime of x. Okay, this is the rule in the general case. Any questions? Like this. Okay, so we can understand now the simple examples given in this part. So 3 to the power x, by the way, here a can be any real number. It doesn't need to be integer, it doesn't need to be rational number, it's any real number. Okay, here in this example, A is chosen as 3. So we will apply this rule, itself times ln 3. But if we put some power here, instead of x, we put 5x, the rule applies itself times ln 3 and the derivative of the power. So f prime of x is multiplied at the end. And similarly, itself times ln 3 and then finally you multiply with the derivative of the power like that. This is the new rule for us. Let me say a few more words on this general exponential function. So a to the power x so we are working on this function, right? And this is called as the general exponential function. What if we choose this number a as the spatial number e? You know the spatial number e, right? So what if we choose a as e, then it becomes a very familiar function for us. Then it becomes e to the power x, which is called as the natural exponential function, okay? Natural exponential function. You see, general case and the particular case where a is chosen as the spatial number e. And let's also recall the derivation rule for the natural exponential function. Everybody knows that its derivative is itself, right? Its derivative is itself, e to the power x. But where does this rule comes from? This rule comes from this very general rule for the a to the power x functions. So I will apply this rule for e to the power x itself times ln e. And we know that ln e is what? What is ln e?
1.
1, thank you. So it is evaluated as 1 because ln and e exponential are inverse functions to each other. That's why they neutralize each other. ln e is 1. So the derivative rule for e to the power x is itself, of course, by using this general rule. Okay, that's all I want to recall you about this general exponential and natural exponential functions and their derivation rules. Now let's use a few minutes on understanding this time general logarithm function, okay? So this is our general logarithm function. There is also the natural logarithm function, which is ln x. So, and there is this passage between general logarithm function and ln function. Log base a of b can be written as ln b over ln a. This is how you transform log to ln, where ln is the natural one and log is the general one. Natural logarithm function is the ln function. Okay, what if we want to take the derivative of log function? There is no special rule for it. I mean, at the end, we will see the rule, but we won't memorize it. Instead, we will use this passage. Okay, let's do it ourselves. So log function, to take the derivative of it, should be transformed to ln function by using this expression. So what is this? This is then ln x over ln 2, right? And then I want to take the derivative of this expression. Now I can handle it because I know how to take the derivative of ln function, and this is just a constant in front. This constant can be moved out from the derivation, and then I just need to take the derivative of just ln. So it goes like 1 over ln 2 times 1 over x, which is the derivation rule for ln x, okay? Every time, when you want to take the derivative of log, you need to transform it to ln, and then you can handle the derivative. Now let's look at this example. What if I change the roles of x and y here? Okay, let's try to handle it again. I changed the roles of x and, not y, sorry, I think I just said y, but x and 2 here. It is transformed to ln. as ln 2 over ln x. And how do you derive this? It is, again, ln 2 goes out, 1 over ln x to the power, derivative of 1 over ln x. How do you take the derivative of this expression? Let me show you here, or let me move on by writing. It is in fact ln x to the power minus 1, and we want to derive it, right? And now you can easily deal with the minus 1 power in taking derivative. So it goes like minus 1 comes down, and then you subtract 1 from the power, and then you also need to multiply with the derivative of the insider function. So 1 over x comes from the derivative of ln x. This whole thing is this derivative, okay? I take the power down, I subtract 1 from the power, and then I multiply it with the derivative of the insider function. Is that okay? Any questions so far?
Is there any more simplification to this?
Is there any what?
Any more simplification to this?
No, I guess. You mean, can we simplify the result? No. And it is the only way to take the derivative of 1 over something. You will think it as ln x to the power minus 1, okay? And maybe we can just put a shortcut here, like how do we take the derivative of 1 over x things? This is x to the power minus 1. And you derive it as minus 1 comes down, x to the power minus 2. So it is, in fact, minus 1 over x squared, right?
Yes.
So that's what we did here. Okay, let me rewrite the result. The result is minus ln, okay, I want to show you. We are, in fact, did this, minus 1 over x squared for ln x. ln 2 is the constant, minus 1 ln x squared, and then we multiplied with the derivative of the ln. Okay?
Okay, thank you.
You're welcome. Okay, I also want to say a few words on natural and general logarithm function inside the recall. So we deal with log base ax function here, right? And I told you that there is a passage to ln function for this one. So this is what we call as the general logarithm function. And if you, just a second, logarithm function, if you insert the spatial number e for a again, as we did here, remember, for the general exponential function, we inserted the spatial number e for a, and we obtain e to the power x. We will do the same. If you insert the spatial number e here, then what happens? Let's see. Logarithm base ax, and let's also insert the spatial number e to this part. Since ln e is 1, you obtain ln x. You see, from natural functions, sorry, from general functions to natural functions, you pass by inserting the arbitrary constant a as the spatial number e. So what you obtain here is the natural logarithm function. Okay, so this is the relation between general and natural ones. The only difference is, in the general case, you can use any real number, but in the natural case, you use that real number as the spatial number e. I guess that's okay, right? Any questions? Okay, so let's move on. Let's look at this example now, which is about taking derivative of ln's. I think I solved the very same example in the recorded video, but let me go over it quickly once again, as we are here together in an online meeting. Okay, recall that, You already know the derivative of ln x is 1 over x. What if I put some function inside ln, depending on x, like f of x? Then you will apply chain rule. Derivative of ln, which is the most outer function, is 1 over whatever you see inside, and then you will multiply with the derivative of the insider function, okay? So let's apply these rules. Y prime is 1 over x cubed. You see x cubed is the insider function, and then you need to multiply with the derivative of x cubed, which is 3x squared, okay? Move on. Please interrupt me whenever you have a question. Y prime, the most outer function here is taking this power, cubed power. So 3 comes down, ln x, I subtract 1 from the power, and then I need to multiply with the derivative of the insider part. Derivative of ln is 1 over x. Move on to, is there any question? Okay, let's continue with the next one. This one, y prime is, start with the most outer function. Okay, derivative of ln is 1 over whatever you see inside. ln x. And then you keep multiplying with the derivative of this insider part. Okay, what is the derivative of this part? It is again 1 over, this time, whatever you see is ln x, times the derivative of this most insider part is 1 over x, okay? So we applied chain rule here. Step by step, we move inside. Okay, next one. Here y prime is given as, again, the most outer function is ln, and its derivative goes like 1 over whatever you see inside of ln function. Like that, and then I need to multiply with the derivative of the insider function, right? Which is this one. So I need to multiply with the derivative of this expression. Okay, let's try to handle this derivative. How can you? You know, this is what? This is x times square root x plus 1 to the power minus 1. And we are trying to take the derivative of it. So let's take the derivative of it. Minus 1 power will move down. Minus 1. I will take the power down. Then I will subtract 1 from the power. And then I will multiply with the derivative of the insider part. You know, this is a product. So I will apply product rule. Derivative of x is 1 times the second expression plus first function stays the same times the derivative of the second one. So this is a square root function and it is derivated as 1 over square root itself times the derivative of the insider part. I mean, derivative of x plus 1 is just 1, right? So that's why I multiplied with 1 here, 1 there. So this whole expression gives you the derivative of this thing. Okay? Can I move on? So minus 1 was the power function there. So I first handled that power function in derivative. And then I multiply with the derivative of the insider part by applying product rule because the insider function was a product. Can I move on? Okay, let's move. This time we have log function, which is the general logarithm function. And to be able to take the derivative of it, you need to transform it to ln. And this is the rule for transforming it, right? ln x cubed plus 5 divided by ln x squared. So we need to take the derivative of this expression. And we should apply quotient rule for it. What is quotient rule? If you have such a ratio and want to take the derivative, it goes like f prime g minus fg prime divided automatically by g squared. So that's what we will apply here. Let's name this f as f and this as g. Derivative of f is 1 over, you know, these are ln functions. x cubed plus 5, 1 over whatever you see inside, times the derivative of the insider part, which is 3x squared. This is f prime times g minus, this time f stays the same, x cubed plus 5 times the derivative of the denominator, which is like that, divided by, you automatically write the square of whatever you see at the denominator. Okay, this is quotient rule. We applied quotient rule here. Is that fine? Okay, what happened here is this is f prime. This is g, where this is f, this is g prime, and this whole thing is, of course, g squared. Okay, let's move on if no questions. We have a log function again. And as I told you several times before, whenever you have natural logarithm, you need to transform that function to, whenever you have log, you need to transform it to ln, and you know how to transform it, right? It is ln of this part, e to the power sine t, ln 3 divided by ln 3. Okay, like that. And for this question, I want to recall you some useful properties of ln function. If you have ln x to the power n, there is a very nice property of ln function here. This power can move down like that. You can take the power down, okay? Other properties, maybe we also need them in the upcoming questions. ln a times b, you can distribute ln products like this, ln a, not directly by putting summation in the middle, and ln also is distributed to the ratios, not directly, be careful, this is not direct distribution, but by putting a minus sign in the middle. This is important, okay? Like this. Okay, let's use this, try to use these properties for this function. You know, ln e to the power something. That's why I can take this power to the bottom, I mean to the base. Like, let me rewrite my function. T times this power comes down like that, and then I have ln e. Denominator is ln 3. We have nice simplification like that. Sorry about that. Okay, what is ln e? It is evaluated as 1. So we realize that the function y is in fact given in this simple form, so that you can easily find the derivative of it by applying product rule, because it's a product. So I'm applying the product rule here. Okay, so derivative of t is 1 with respect to t times the second function plus first function stays times the derivative of the second function, which is cosine. So that's it. After transforming log to ln, then you are allowed to use the properties, nice properties of ln function, and then we obtain some very nice simplifications so that y turns out to be this simple function, which is just a product of two functions, and we can easily derive it. Any questions? Okay, then let me also solve this question for you before the break, and then we can take a nice break. Okay, again, log function we have, and we have another complicated expression here. Let's start by transforming log to ln. This will always be the first step for you if you have log and want to find the first derivative of your function. ln of, okay, ln of this whole expression divided by ln 5. And you see this square root here, right? Can I write it as a power? Let's try to write this square root as a power. So then what should I write for the power of this expression? It is ln 5. How can I insert this square root to this power?
Divided by 2.
Exactly, divided by 2. Okay, I did it like that because I want to use this very useful power rule of the ln function, which I recalled you here. If you have ln x to the power something, that something comes down. So this will move downstairs. Okay, then the y function is ln 5 over over 2, not ln 2, over just 2, times ln. Now I will also apply, okay, let me first write and then we can rewrite it. I will also apply this quotient rule of ln in the next line. Let me simplify this ln 5s, then y function, sorry, this is not derivative yet. We are still trying to simplify y function. We have 1 over 2 as a coefficient. So ln a over b form we have. So this is in fact ln this minus ln of the denominator. So this is what we have. Then you see, instead of writing y in a very complicated form like that, you can just write it like this. So it is a bit surprising, right? These two expressions are the same. Here, it looks like very complicated, but here, in fact, it is much more simpler if you do the possible simplifications. Okay, so now I am ready to take the derivative of it. Derivative of ln 7x is 1 over 7x times the derivative of the insider function, which is 7 minus 1 over 3x plus 2. By the way, these are inside ln function, all of them. So times the derivative of the insider function, which is 3. Okay, that's the first derivative of y. If you transform it to this simpler form by using, first by transforming log to ln like that, and then using several properties of ln, you obtain this simpler form, and that's the derivative of it. I think I will stop here for the break.